In the dark, crushing depths beneath the ocean floor, where water pressure can flatten steel and a single crack means catastrophic flooding, China is building something that has left American engineers speechless. Undersea tunnels stretching over 5,000 meters through solid rock beneath the sea. These are not ordinary tunnels. These are massive underwater highways carrying thousands of vehicles daily through passages carved beneath millions of tons of seawater. Passages where the ocean above is constantly trying to break through and reclaim what was taken from it. The engineering required is so extreme that even a 1 millimeter miscalculation could trigger a chain reaction of failures. Water seepage becomes flooding, flooding becomes collapse, and collapse beneath the ocean means there is no escape, no second chance, no margin for error whatsoever. Yet China has not built just one of these tunnels, it has built dozens, each one longer, deeper, and more technically ambitious than the last, each one pushing the boundaries of what engineers believed was physically possible beneath the sea. The numbers are staggering. Some of these tunnels stretch beyond 5,000 meters in length. They plunge more than 50 meters below the seabed. They cost billions of dollars and take nearly a decade to complete, and they operate 24 hours a day, every single day. When American engineers first reviewed the technical specifications of these projects, many openly admitted they had never seen anything like it. The scale, the precision, the speed of construction. China was not just building tunnels, it was rewriting the engineering rulebook entirely. But how do you build a tunnel beneath the ocean? How do you keep millions of tons of water from crushing everything inside? How do you dig through unknown geology while the sea presses down from above with relentless, unforgiving pressure? This is that story. Every undersea tunnel begins not with construction, but with years of painstaking investigation. Engineers must understand exactly what lies beneath the seabed before they commit billions of dollars and thousands of lives to digging through it. The unknown is the enemy. Specialized survey vessels spend months mapping the ocean floor above the proposed tunnel route. Sonar systems bounce sound waves off the seabed, creating detailed three-dimensional maps of every ridge, valley, and geological formation. Nothing can be left to assumption. Then come the drilling ships. Geotechnical rigs lower rotating drill bits through hundreds of meters of water and into the seabed below. They extract cylindrical core samples that reveal every layer of sediment, clay, rock, and potential hazard hidden beneath the ocean floor. Marine geologists analyze these cores layer by layer. They identify fault lines where earthquakes could strike. They locate zones of fractured rock where water could pour in uncontrollably. They map underground rivers and pockets of pressurized gas that could explode during excavation. The data is fed into massive computer simulations. Engineers build complete digital models of the tunnel route, testing thousands of scenarios. What happens during an earthquake? What happens if they encounter unexpected water? What happens if the rock is weaker than predicted? Only when every question has been answered and every risk has been calculated does the actual construction planning begin. In China, this investigation phase alone can take 2 to 3 years because beneath the ocean, you do not get the luxury of learning from mistakes. China uses 2 primary methods to build undersea tunnels. The first is the immersed tube method. The second is tunnel boring machines. Each method has specific advantages, and each presents its own terrifying challenges when applied beneath millions of tons of ocean water. The immersed tube method begins not underwater but on dry land. Massive reinforced concrete tunnel sections are constructed in specially built dry docks along the coastline. Each section is enormous. Some measure over 180 meters long and weigh more than 80,000 tons. Inside each section, multiple compartments are precision-engineered: lanes for highway traffic, space for railway lines, service corridors for maintenance and emergency access, ventilation shafts, electrical conduits, fire suppression systems, everything a complete underground transportation system requires, built into each segment. The construction tolerances are extraordinary. Every surface must be smoothed to within millimeters. Every joint must align perfectly with neighboring sections. Every waterproofing layer must be flawless, because once these sections are underwater, any defect becomes a potential catastrophic failure point. Steel reinforcement cages containing hundreds of tons of rebar are assembled inside each section. Concrete is poured in carefully controlled stages to prevent cracking from heat buildup during curing. The concrete itself is specially formulated to resist saltwater corrosion for over 100 years. Waterproofing is applied in multiple redundant layers. First, a primary membrane of synthetic rubber sheeting, then a secondary layer of bituminous coating, then a tertiary protection of steel cladding. Each layer is independently capable of keeping the ocean out. Together, they create an almost impenetrable barrier. Once a section is complete, the dry dock is flooded. The massive concrete tube, designed to be slightly buoyant with its temporary end cap sealed, begins to float. Tugboats attach heavy cables and slowly, carefully tow the section out to the open sea. Navigation during transport requires extraordinary precision. The section must travel along exact predetermined routes, avoiding shallow areas, other vessels, and underwater obstacles. GPS systems track position to within centimeters. A single collision or grounding could crack the waterproofing and doom the entire section. At the installation site, a trench has already been dredged into the seabed. Massive cutter suction dredgers have carved a precise channel matching the exact dimensions of the tunnel sections. The trench walls are reinforced with rock to prevent collapse during installation. The section is positioned directly above its target location using GPS and underwater acoustic positioning systems. Then, the controlled sinking begins. Water is gradually pumped into ballast tanks inside the section. Slowly, the enormous tube descends through the water toward the waiting trench below. Divers and remotely operated underwater vehicles guide the section into position. The precision required is almost unbelievable. The section must align with the previously installed segment to within 25 millimeters. Underwater, in currents, with thousands of tons of concrete slowly sinking. Once positioned, the section is pressed against the previous one using hydraulic rams. The joint between sections is the most critical point in the entire structure. Rubber gaskets compressed between the concrete faces create the primary water seal. Then the space between is dewatered and inspected. Workers enter the joint space and apply additional waterproofing. Concrete is poured to permanently bond the sections together. The temporary end bulkheads are removed, connecting the interior spaces. What were separate floating tubes are now a continuous sealed tunnel resting on the ocean floor. Sand and gravel are then placed over and around the completed tunnel sections. This backfill protects against anchor strikes from ships above. It provides additional weight to prevent buoyancy forces from lifting the tunnel, and it shields the structure from ocean currents that could erode its foundation. The second method China uses is the tunnel boring machine. These are the largest, most complex machines ever built by humans. Some measure over 15 meters in diameter and stretch longer than a football field. They are underground factories that eat rock and leave finished tunnel behind them. The cutting head at the front of the machine is a rotating disc studded with hundreds of hardened steel or tungsten carbide cutting tools. As it spins under enormous hydraulic pressure, these tools grind through solid rock at rates of up to 20 meters per day.
Behind the cutting head, a complex system of conveyor belts carries the excavated rock and sediment backward through the machine and out of the tunnel. Thousands of tons of material must be removed every single day. The logistics of waste removal alone require dedicated engineering teams. As the machine advances, it simultaneously installs the tunnel lining. Precast concrete segments are lifted into position by hydraulic arms inside the machine. These segments lock together, forming a continuous ring that supports the surrounding rock and prevents collapse. Each ring is waterproofed before the next is installed. The machine operates under the most extreme conditions imaginable. Water pressure from the ocean above presses down constantly. The cutting face can encounter unexpected geological changes without warning. Hard granite can suddenly give way to soft clay or pressurized water zones that flood the excavation chamber. To combat water pressure, the tunnel boring machine operates behind a pressurized shield. The excavation chamber at the front is filled with pressurized slurry or compressed air that balances the water and earth pressure outside. If the pressure drops even slightly, water rushes in. Workers inside the machine operate in conditions that would terrify most people. The noise is deafening. The heat from friction and machinery reaches extreme levels. The air is thick with dust and humidity, and they work knowing that millions of tons of ocean sit directly above their heads. Emergency systems are extensive. Pressurized refuge chambers provide safe zones if water breaks through. Redundant pumping systems can remove thousands of liters per minute. Communication systems maintain constant contact with surface control rooms. Escape routes are maintained and drilled regularly. When the tunnel boring machine completes its journey, breaking through into the receiving shaft on the opposite shore, the celebration is enormous. But the tunnel is far from finished. The raw excavated tube must now be transformed into a fully functional transportation corridor. Interior construction begins immediately. The rough concrete lining is coated with additional waterproofing membranes. Smooth interior walls are installed. Road surfaces are laid. Lane markings are painted. Lighting systems capable of illuminating kilometers of tunnel are installed along the ceiling. Ventilation is critical in undersea tunnels. Vehicle exhaust must be removed and fresh air supplied continuously. Massive fan systems capable of moving millions of cubic meters of air per hour are installed. In emergencies, these systems can reverse airflow to push smoke away from trapped vehicles. Fire suppression systems are installed every few meters throughout the tunnel length. Heat sensors and cameras monitor every section continuously. Emergency exits and cross passages connect parallel tunnel tubes, allowing evacuation from one tube to the safety of the other during emergencies. Drainage systems handle the constant battle against water infiltration. Even in perfectly sealed tunnels, small amounts of water seep through over time. Collection channels run along both sides of the roadway, directing water to pumping stations that operate continuously, removing thousands of liters every hour. Electrical systems power everything from lighting to ventilation to emergency systems. Redundant power supplies ensure that a single failure never causes a total blackout. Backup generators can maintain critical systems for days. Every electrical component is rated for the extreme humidity of the undersea environment. Traffic management systems control vehicle flow through the tunnel. Speed cameras and sensors monitor every lane. Variable message signs communicate with drivers. In emergencies, automatic barrier gates can seal the tunnel entrances within seconds, preventing additional vehicles from entering a dangerous situation. Seismic monitoring is essential for tunnels in earthquake-prone regions. Accelerometers embedded throughout the structure detect ground movement instantly. If vibrations exceed safe thresholds, automatic systems can close the tunnel to traffic within moments, protecting thousands of people from potential structural compromise. The completed tunnel undergoes months of testing before opening to the public. Engineers flood sections to test drainage capacity. Fire drills simulate worst-case emergency scenarios. Ventilation systems are pushed to maximum capacity. Structural sensors are calibrated and verified against computer models. Every safety system is tested to failure point and beyond. Emergency lighting must function for 72 hours without external power. Communication systems must work through solid rock and water. Evacuation routes must accommodate the maximum number of occupants within certified time limits. China's Taihu Lake Tunnel stretches over 10 kilometers beneath the water. The Jiaozhou Bay Tunnel near Qingdao extends nearly 7 kilometers, connecting the city to its western development zone. The Xiang'an Tunnel in Xiamen was the first large-diameter undersea tunnel built in mainland China. But the most ambitious project is the planned Bohai Strait Tunnel. If completed, this undersea crossing would stretch over 120 kilometers beneath one of the busiest shipping channels in Asia. It would be the longest undersea tunnel ever attempted in human history. The Bohai Strait Tunnel would connect Dalian in the north to Yantai in the south, cutting travel time from the current 7 hours by ferry to just 40 minutes by high-speed rail. The economic impact would transform the entire northeastern Chinese economy.
American engineers who have studied these projects express both admiration and concern. Admiration for the technical achievements and construction speed. Concern that the sheer ambition of these projects may outpace the safety margins that decades of Western engineering experience have established as essential. The speed of Chinese tunnel construction is particularly striking. Projects that American engineers estimate would require 15 to 20 years are completed in China in 7 to 10. This acceleration raises questions about quality control, long-term durability, and whether shortcuts compromise safety. Yet the operational record speaks volumes. Chinese undersea tunnels carry millions of vehicles annually, with safety records comparable to international standards. Continuous monitoring systems detect problems before they become dangerous. Maintenance programs address wear and deterioration systematically and proactively. The engineering innovations developed for these tunnels are now being exported worldwide. Chinese tunnel boring machines are operating in dozens of countries. Chinese construction techniques are being studied and adopted by engineering firms across Asia, Europe, and increasingly in the Americas. For the thousands of workers who build these tunnels, the work carries profound meaning. They descend beneath the ocean every day, knowing the risks. They work in conditions that would break most people. And they emerge having created something that connects cities, transforms economies, and outlasts generations. The tunnels they build will carry millions of people safely beneath the waves for decades to come. Invisible to the passengers who speed through them, taken for granted like roads and bridges on the surface. But beneath the ordinary experience lies extraordinary engineering achievement. Every vehicle that passes through an undersea tunnel drives through a space that was once solid rock beneath millions of tons of ocean. A space carved by human hands, sealed against impossible pressure, and maintained by constant vigilance against the sea that never stops trying to reclaim it. China has proven that the ocean floor is not a barrier, it is a frontier. And with enough engineering brilliance, enough determination, and enough courage, even the deepest waters can be crossed. Not over the waves, not around them, straight through the earth beneath them. What do you think about China's undersea tunnel engineering? Does their speed and ambition inspire you or concern you? Share your thoughts in the comments below. And if this story amazed you, subscribe and turn on notifications so you never miss another incredible engineering story.